Dear learners, in this portion of the lecture, I am going to focus on the measurement noise. In the previous lecture, I talked about how noise or error can be induced into our measurement system. There are primarily two different areas or two different situations where error can be induced. The first one is when you are taking the measurement or during the measurement process. And the second one is when you are routing or transmitting the measured signal from the sensor to some remote location or to some other part of the circuit. In this portion of the lecture, I'm going to talk about the noise or error that can be induced into our sensed signal when you are moving that signal from one place to the other place. It can be from the sensor to some processor, or it can also be from one processor to some remote processor or logging facility. Majority of the noise that is induced in this situation is coming from interference from other components of the measurement system or from some components that are placed or are lying near our measurement system. I'm going to talk about a number of external sources from which noise may be induced into the signal wire and ultimately corrupt our signal. The first one is inductive coupling. You must remember from your physics class that what is a couple. When a torque is acting at some body with equal strength at two different ends such that it is rotating or trying to rotate that body about a pivot, then those torque vectors are called couples because they are equal but are acting at opposite ends of whatever object you are considering. In inductive coupling, what happens is that the signal carrying wires become coupled with another electrical wire that is carrying some other signal or any other electrical supply. When the current is flowing in one wire, it may be induced through the principle of mutual induction into the other wire. You already know that how this induction takes place. I've written the formula over here just for your reference. This kind of induction is of several millivolts, and hence if the signal which the sensor has generated was of the order of millivolts, it can be easily corrupted by this mutually inducted unwanted signal or voltage. Just as inductive coupling can develop between two wires, capacitive coupling can also develop. A capacitor is nothing but two metal plates separated by a dielectric. So what if one cable is acting as a metallic plate whereas another cable is acting as another metallic plate and the gap or the air between them is acting as a dielectric? So it will become a capacitor. This capacitance will generate a charge that will be stored on the electrical plates or in this case on the cables. In the figure shown, you can see that there are four different places where this kind of capacitance can develop. Another common source of error that may induce noise into the captured signal is the use of multiple earths. Normally, a student project is affected by this kind of problem quite often. There are two different things to consider over here. The first one is that all the components carrying approximately equal amount of currents and voltages must have same earth. If they have different earths, then it would mean that they might have different reference voltages. And if any earth is at a different potential than the other one, then the signal between the wires may not be compared with each other. And the other case would be that if you are using same earth for a high current carrying wire and a low signal carrying wire, the high current carrying wire will change the potential of the earth and hence will disturb the reference of the signal carrying wire. So our common practice is to have a separate ground or earth for all low current carrying wires while a different earth or ground for a high current carrying wires. I will discuss this thing once again in the later section of this lecture, and I hope that it will become more clear over there. The next source which I am going to discuss is of voltage transient. Normally when a heavy electrical machine starts or stops, a large change of power consumption occurs. This large change in power consumption induces voltage transients or sometimes back EMF in the electrical supply. You might have seen this thing in your home that whenever a water pump or a compressor of your AC turns on, all the lights in your room suffers a minor fluctuation. This fluctuation is because of the voltage transient that pump or the compressor has induced into the system. Corona discharge is a common problem, but normally a mechatronics engineer or an instrumentation engineer doesn't face this kind of problem because this thing happens at a very high voltage. When a conductor carrying a very high voltage ionizes the air or fluid present around it, some charge may leak into that ionized air. In the figure shown, you can see that there are some hot spots. These hot spots are depicting the leaked charge from a high voltage carrying conductor. You won't be able to see this kind of effect with your naked eyes. You need special imaging devices, normally called thermal imaging devices, to see this kind of effect. Now I'm going to talk about the thermoelectric effect or the thermoelectric potentials that are generated. I hope that you have already heard about it. What happens in a thermoelectric effect is whenever two metals of different types are connected together, a thermoelectric potential is generated according to the temperature of that joint. What is happening at that joint is there are two different conductors, both at same temperature, but both having different kind of electron activity at that temperature. For example, whatever electron activity copper has at 30 degrees, tin will not have that electron activity. So if you join both of them, then some free electrons will move from one wire to the other, depending on the amount of electrical activity in those wires. Such thermoelectric potential is of the order of few millivolts, and we will study that this thermoelectric potential can be very useful and can be used to measure the temperature at which the joint is currently present. So we have a temperature sensor that is called a thermocouple that is relying on this principle only. But that would be left for some later lecture where I will explain the working principle of a thermocouple thermometer. So whenever you are joining two wires or soldering a wire to the board, a junction will be made. At this junction, depending on the temperature and the metals which you are using, some thermoelectric potential may develop. And this will definitely interfere with the signal that is carried by the signal wires. Short noise is relatively rare kind of source of noise. It can be seen wherever transistors or some other semiconductor devices are used. As you know that semiconductor devices are PN or NPN or PNP junctions in which electron hole pairs are moving. So if there is any random fluctuation in the rate of transfer of these carriers across the junction, then that random fluctuation will act as a noise. Ideally, constant rate of transfer of carriers between the junctions should occur, but the world isn't ideal at all. So I have discussed a number of sources through which noise may be induced into the signal carrying wire and hence crippling the signal. So what are the ways to avoid this induction of noise? There are several practices that are related to design and some are related to the use of the equipment that can mitigate the induction of this kind of noise. To start with, the mutual inductance and capacitance between signal wires and other cables is known to be inversely proportional to the square of the distance between the wires. That is, if you increase the distance between the wires, the mutual inductance and capacitance will abruptly decrease. Therefore, you can easily make sure that there is no inductive or capacitive coupling between the wires by placing them far from each other. A normal practice is to place the signal carrying wire and the main electrical wire at least zero point 0.3 meters away from each other. However, a separation of 1 meter is preferable. Another way of reducing the noise induced due to inductive coupling is to use twisted pair of wires. In the diagram shown, you can see that if you are using two wires A and B, then in this junction, V1 will be induced in the wire A, whereas V2 will be induced in the wire B. However, in the next area, which is this one, V1 will be induced in wire B, whereas V2 will be induced in wire A. So at the end, both wires will have same noise induced because of the inductive coupling. At the end, we can use a differential amplifier or an instrumentation amplifier that we will study in some later lecture to remove or reject the common signal present in the wire. And hence, noise can be reduced or eliminated because it is the only common thing in the two wires. As far as noise due to multiple earths is concerned, I've already discussed that how you can tackle this kind of problem. In practice, there are four different kinds of earth that are used and should be properly separated from each other. The first one is the power earth, that is the path for all the fault currents that are generated due to power faults. The next one is called the logic earth, and it is the earth that is used for all logical signals, or you can also say for digital signals. Logical signals are normally binary signals, that is, they have two levels. For example, -3 volts and +5 volts. Then comes the analog earth. This analog earth is specifically called ground. It provides a reference for all the analog components or the analog signals in the circuit. Therefore, you can also say that the digital circuits are being referenced from the logic ground, whereas the analog components are being referenced from the analog earth or the ground. And at the end, there is a safety earth. The safety earth has all the metal parts of the equipment connected to the ground, so that if by accident any metal part comes in contact with a live wire and there is a possibility that human may touch that metal part, then the current should not flow through the human but through the metal part to the safety ground, hence tripping the electrical system behind the device. Another way to reduce the measurement noise is to enclose the signal wire in an earth metal shield that is itself isolated electrically from the signal wires. A shield in this case is normally made up of braided metal and lap metal foil. You must have seen this kind of shielding around the coaxial cable that is used to carry the cable TV signal and sometimes the internet signal as well. It is established that the braided metal eliminates 85% of the noise due to capacitive coupling, whereas a lapped metal foil can eliminate it completely. So, a coaxial cable of lower quality will definitely have a braided metal shield, whereas an expensive cable will have both braided metal and lapped metal foil. And furthermore, inside these shields, normally a twisted pair cable is used so that any noise from electromagnetic field may also be eliminated. So, dear learners, this was everything about the sources of noise and how we can try to remove the noise being induced from these sources into our signal. I hope you have understood the types of noise and the sources of noise and ways to reduce that noise. Over here, I would ask you guys to think of or to find any signal present around you that is normally corrupted by noise. That is, whenever you generate the signal, it is generated correctly, but during its transmission, it gets corrupted. So think of such a situation and write it down in the comments below. So this was everything from my side. Thank you and goodbye.